I'm so upset that I think it's gonna rain on
Morning, everybody. Do you guys hear me? Okay. All right. So I think for exam, you guys all got great, right? And I just posted the score distribution. I think you guys overall, did pretty good. The mean is like 40.99, and standard deviation 6, I guess, 0.35 or something like this, but pretty good. Um, okay, so today we're going to start talking about lipid metabolism. So lipid metabolism also includes the several different metabolic pathways, right? Like biosynthesis of lipids and oxidation of lipids break down the triglyceride, oxidized fatty acids, and also ketone body synthesis, a cholesterol synthesis pathway, right? And today we're going to start with the biosynthesis of fatty acids and triglycerides. So lipids, we know the major lipids in our body include lipids present in the plasma or the tissue cells, and this will include free fatty acids, monoacylglyceride, and diacylglyceride, and triglyceride, right? And also we have other type of lipids like cholesterol esters, phospholipids, sphingolipids, and other intermediates of lipid metabolism, right? And sources of plasma tissue lipids are basically as the two major sources, right? One is from the diet. We can absorb the lipids from the diet, right? So, and the other major source is the synthesized in our body. So our body and also able to synthesize lipids. So biological role of lipids, several roles, and most important roles of lipids is as an energy source, right? For example, triglyceride. So we use triglyceride for energy, for ATP production. It is actually a very important way to store lipids as energy. For example, the 1 gram of, sorry, the 9 kcal per gram of fat. So if we burn or utilize 1 gram of fat, we're able to generate the 9 kcal energy, right? And compared to only 4 cal energy per 1 gram of carbohydrate proteins, right? So it's more efficient energy that can be used in our body. And the second important role of the lipids is as a structure component of membrane, like cell membrane or intracellular organelle membranes are all consist of the phospholipids, right? So the lipids is also important structure components of a biological membranes. And lubricant. So it is, we need the lipids to conditioning the body cell surface, right, or something like this. And the last one actually is very important. Recently, gain a lot of attention because of some of the lipid intermediates play a very important role as a signaling molecule, so can regulate the body, whole body metabolism. I just take one example, the ketone bodies, right? Usually people think ketone body just as alternative fuels, right? Use it for the energy production, but recent years, the the researchers found ketone body is also very important to regulate metabolic activities, right, as a signaling molecule. And some of the lipid intermediates can also be used for synthesis of sex hormones and and vitamin D even. So now let's start talk about synthesis of lipids. So synthesis of lipids, I wanted you guys to not to be confused. Fatty acid synthesis versus triglyceride synthesis, right? It's actually two different concepts. So the fatty acid synthesis, we start from acetyl-CoA, very small molecules, right? And so acetyl-CoA can be used to synthesize fatty acids, the long-chain fatty acids. And triglyceride synthesis means that the glycerol backbone together with the three fatty acids, right, to form triglyceride. So it's a different concept, right? So I just want to remind you again, this is the molecules of the triglyceride, right, with a glycerol backbone and three free fatty acids attached to the glycerol backbone and forming triglyceride, right? So fatty acids synthesis, sometimes we also call it de novo synthesis of fatty acids or lipogenesis, right? So lipogenesis or de novo fatty acid synthesis refers to the fatty acids synthesis, right? So lipogenesis or de novo fatty acid synthesis, the primary tissue, which tissue you would think the fatty acids or lipogenesis occurs? Which tissue is the most important? Liver? Oh, it's already in the notes, right? Huh. I should not put that. Liver and adipose tissue, right? So why we put the liver first? Liver is more important than the triglyceride in terms of fatty acid synthesis, right? But adipose tissue is more important for triglyceride synthesis, right? So it's different concept, right? The liver is a primary tissue for lipogenesis, and lipogenesis can also occur in the adipose tissue, but relatively small scale compared to liver, right? And second point is a high-fat diet. It's also in your notes? No? Okay, that's good. So high-fat diet. How do you think high-fat diet regulates lipogenesis? Sorry? Decrease? Yes. Decrease lipogenesis, right? Do you guys all agree? Yes? Okay, that's good. So high-fat diet actually decreases or suppresses lipogenesis. How? Why? How? I mean.
If the body is obtaining it from outside, doesn't need to process it?
Yes, that's the general, yeah, in general. But we wanted to understand a little bit detail, the molecular mechanism, how. But we're going to get there, right, later. Just keep in mind, this kind of question, why a high-fat diet will suppress or inhibit lipogenesis, right? And how about a high carbohydrate diet? How carbohydrate diet to do with lipogenesis? Should be increasing, right? Should increase lipogenesis. And I think we mentioned earlier that carbohydrate diet, particularly high sucrose diet, will increase the lipogenesis, right? So carbohydrate, if we intake too much, then we'll convert it to fat, right? So carbohydrate diet basically stimulates lipogenesis. Okay, so the last point, what we try to say here is that the lipogenesis or de novo lipogenesis may not contribute significantly to triglyceride synthesis when we consume a Western diet, meaning the high-fat diet. Right? High-fat diet basically inhibits, right, the lipogenesis, but it does actually contribute to the. Sorry, I want to say that. I mean, it's high fat diet does not contribute to lipogenesis, right? Okay, so what is the purpose of lipogenesis? Why we wanted to do the lipogenesis? Particularly when we eat a meal, right? We have a surplus carbohydrate and proteins. We can't use them all, right? So we wanted to store this extra energy in the body, so convert the extra carbohydrate protein into the fat and store in the form of triglyceride in adipose tissue. So this is the main purpose that our body does lipogenesis, right? Particularly that is happening in the fat condition, right? And it is particularly when we eat a high carbohydrate diet. So high carbohydrate diet can strongly stimulate lipogenesis. So where does lipogenesis take place in the cell? Cytosol versus mitochondria. Just remember the oxidative or metabolism or like catabolic metabolism usually takes place in the mitochondria, right? So this is synthesis, right? So consider the anabolic metabolism. So it's in the cytosol. So lipogenesis takes place in the cytosol, in the cell. And what are the building block molecules of fatty acids? The smallest molecule that can be used for fatty acid synthesis I just mentioned. Acetyl-CoA, yes. Acetyl-CoA is this building block molecules or starting molecules for fatty acid synthesis, right? So fatty acid synthesized from acetyl-CoA. So because of, we just mentioned that the lipogenesis process converts surplus glucose and its metabolic intermediate to fat. So the precursors for de novo fatty acid synthesis are glucose, pyruvate lactate, acetyl-CoA, right? So any molecules or nutrients that can be metabolized to acetyl-CoA that are able to be converted to the fatty acids, right? So precursors can be glucose, pyruvate lactate, and acetyl-CoA. So don't be confused with the starting molecules, right? Starting molecules is acetyl-CoA, but precursors, that means these molecules or intermediates can be converted to, can be metabolized to acetyl-CoA and used for fatty acid synthesis, right? And starting molecule is acetyl-CoA. And here I just wanted to take like one example. So end product is palmitate. Palmitate is saturated fatty acids with 16 carbons, right? So 16 carbon saturated fatty acids. And its location, fatty acid for fatty acid synthesis is in the cytosol, and the primary tissues for lipogenesis is liver and adipose tissue, right? And nutritional status that promotes lipogenesis as well, fat, high carbohydrate, and under fat condition, right? So this is just the overall picture of the lipolysis. For example, when we consume a high carbohydrate diet and our blood glucose levels increase, right? And that will stimulate insulin secretion. So insulin level is very high under the fat condition, particularly high carbohydrate diet. And also we have an increased substrate level. For example, glucose level will be very high, right, in the circulation. So all these conditions will together promote lipogenesis. So again, lipogenesis mostly occur in the liver. So liver picks up the glucose, right, or even some amino acids, right, and metabolize and convert it acetyl-CoA and for fatty acid synthesis. And once fatty acid is synthesized in the liver, then it's used for synthesize triglyceride, and triglyceride is usually liver does not store a lot of triglyceride, right? And adipose tissue is a place for triglyceride storage. So the triglyceride is synthesized from fatty acids initially from carbohydrate or protein that in the liver need to be transported to the adipose tissue for storage. And this transport process requires a group of protein called lipoprotein, right? We have a specific session to talk about the lipoprotein, but just wanted to give you kind of idea, the triglyceride transported from liver to adipose tissue requires the lipoprotein, right, to help the triglyceride transport. And again, the liver is a primarily tissue for fatty acid synthesis, and the adipose tissue is a primary tissue for triglyceride synthesis, right? And the lipogenesis also occur in the adipose tissue, but in a much smaller, scale compared to liver. And muscle can also does some lipogenesis, right? You have a question?
So triglycerides are made in the liver.
Yeah.
They're not made in adipose tissue. They're made in the liver and then brought to adipose.
Okay, that's a good question. So they're made in the liver, but also in the adipose tissue. For example, the liver triglyceride, right, is transported by VLD, or very low density lipoprotein, carry the triglyceride from the liver to the adipose tissue, and before adipose tissue you take up the triglyceride from the VLDL, triglyceride has to be break down again to the fatty acids because triglyceride is too big, right? Small fat cell cannot take it up. So triglyceride need be break down again to free fatty acids and the triglyceride. So adipose tissue is able to pick up or take up the free fatty acids into the adipose tissue, and then free fatty acids will together with glycerol and synthesize the triglyceride again, right, in the adipose tissue. So this is the whole process. So both liver and triglyceride can be synthesized. Triglyceride can be synthesized in both liver and adipose tissue, but adipose tissue is a major, the main site for the triglyceride synthesis, right? Does that make sense? Okay, so again, we first of all we just wanted to take a palmitate synthesis as an example to to talk about fatty acid synthesis. So for making a palmitate, saturated fatty acids, we need acetyl-CoA, right, as a building blocking molecules, the starting molecules, and requires the other compounds, for example, NADPH that we mentioned, right? Remember the pentophosphate pathway that make the NADH that is needed for fatty acid synthesis, right? So here, fatty acid synthesis requires NADPH, and of course ATP and some metal and biotin and bicarbonate, and most importantly, the two enzyme complexes are required for fatty acid synthesis for synthesized palmitate, right? So one enzyme complex is called acetyl-CoA carboxylase, ACC, and the other complex is fatty acid synthesis complex, right? So ACC, acetyl-CoA carboxylase, is a rate-limiting reaction or key reaction in the fatty acid synthesis pathway, right? So try to remember this, right? The key reactions. Okay, so citrate shuttle, because fatty acid synthesis occurs in the cytosol, right? And where is acetyl-CoA produced? Remember? In which? When we talk about oxidative metabolism, glycolysis, PC cycle, where is the acetyl-CoA generated or made? Yeah, TC cycle. I mean the where, in which cellular compartment? Remember? Pyruvate entered mitochondria and converted acetyl-CoA, remember? Acetyl-CoA entered TC cycle. Yes, mitochondria. So acetyl-CoA is made in the mitochondria, right? But it's needed for fatty acid synthesis in the cytosol. So the important thing is that acetyl-CoA molecule has to be transported from the mitochondria to the cytosol, right? And acetyl-CoA is not permeable to the mitochondrial membrane, so that need a shuttle system to transport acetyl-CoA out of mitochondria to the cytosol for fatty acid synthesis. So this is the citrate shuttles. So the citrate shuttles is important that facilitate acetyl-CoA to move across in a mitochondrial membrane to the cytosol, right? So for fatty acid synthesis. So here is the the diagram to show you how acetyl-CoA is made in the mitochondria, right? This is the mitochondria. This is part of the cytosol. So pyruvate can be generated from glucose oxidation as well as amino acids oxidation, right? Pyruvate enter the TC cycles, and this is a reaction, the pyruvate dehydrogenase, right, to remove the carboxyl group from the pyruvate and convert it to acetyl-CoA. So acetyl-CoA enter the TC cycles. This is the first reaction. Remember TC cycle, right? And together with oxaloacetate and convert it to citrate. And citrate and then move out of the mitochondria by the transporters called tricarboxylate transporter, right? So this transporter also called citrate shuttles, right? Can transport the citrate out of mitochondria to the cytosol. At the meantime, it have exchange with the one molecules of malate. So malate is transported in and citrate transported out by this tricarboxylate transporters, right? So so this is sort of the citrate shuttle system. As the main purpose is to transport acetyl-CoA, right? And in the cytosol, citrate then be break down again to acetyl-CoA by the ATP citrate-lyase enzyme, right? To break down citrate into acetyl-CoA and oxaloacetate again, right? And then acetyl-CoA then enter the fatty acid synthesis pathway in the cytosol, right? That makes sense? Okay, so yes.
So then citrate can get converted to acetyl-CoA in the cytosol?
Right. So citrate again, once it's in cytosol and can be cleaved, right, and release the acetyl-CoA and oxaloacetate by this enzyme ATP citrate-lyase. So ATP citrate-lyase, because ATP citrate-lyase only present in the cytosol, right? So that's the reason why citrate in the mitochondria will not be breakdown to acetyl-CoA or oxaloacetate again.
It just arrives, it stops at malonyl-CoA or at acetyl-CoA?
Malate? I'm sorry, what did you say?
It stops at acetyl-CoA or malonyl-CoA? Because it continues there from acetyl to malonyl.
Which part?
At the top, it says acetyl-CoA and then it points up to...
Oh, malonyl-CoA. Yeah. We're going to talk about the next slide. This is the part of the fatty acid synthesis pathway, right?
Okay.
So the first reaction or step in the fatty acid synthesis is a conversion of acetyl-CoA to malonyl-CoA. So malonyl-CoA is synthesized, is the first step of fatty acid synthesis, right? Yeah, thank you for pointing that out. Okay, so this is the malonyl-CoA production. Again, is the first step in the fatty acid synthesis pathway, right? And this step is catalyzed by a key or rate limiting, or called initial controlling. The similar, right? The rate limiting, a key reaction in the fatty acid synthesis. So this step is controlled by acetyl-CoA carboxylase, or ACC, by this enzyme complex, right? So ACC enzyme complex, the main function of this enzyme is to catalyze the formation of malonyl-CoA from acetyl-CoA, right, by adding one carbon skeleton to the acetyl-CoA, forming 3 carbon molecules, right? Malonyl-CoA is the 3 carbon molecules, and acetyl-CoA is the 2 carbon molecules, right? So the overall these steps had, the ACC is actually multi-enzyme complex, has 3 enzyme protein. One is called biotin carboxylase, and second one is biotin carboxyl carrier protein, and the last one is transcarboxylase, right? So 3 enzymes form the ACC complex, right? And these 3 enzymes work together to catalyze formation of malonyl-CoA. And this step we can divide it into actually two steps, right? This reaction divided, has 2 steps. So first is the transfer of the carboxyl to biotin. So this enzyme means this ACC enzyme complex, right? So biotin attached to the ACC enzyme complex. And first of all, carboxyl group is added to biotin, And this carboxyl group initially come from bicarbonate, right? So that's why we need bicarbonate for this reaction. So an enzyme involved this or catalyze this transfer of a carboxyl group to biotin include the biotin carboxylase and the biotin carboxyl carrier protein, right? So this is the first step in this reaction, key reaction. And the second step that the carboxyl group is then transferred to the acetyl-CoA molecules from biotin, right? So and then once it's carboxyl group is added to acetyl-CoA, then you have one more carbon, right, in the acetyl-CoA molecule and forming the malonyl-CoA. So malonyl-CoA again have 3 carbons and acetyl-CoA 2 carbons. And the one carbon carboxyl group initially is transferred from bicarbonate, right? And this second steps that involved 2 enzymes, bicarbonate carry biotin carboxyl carrier protein and transfer carboxylase, right? So that clear? So again, this is a multi-enzyme complex catalyze the 2 steps of reaction, right? Yes.
If we just need acetyl-CoA to make fatty acid synthesis, why are we trying to make malonyl?
Yeah, so that's, yeah, that if we're going to go on, I mean, we would, understand, actually, as a malonyl-CoA is 2 carbon donors for the rest of the process of fatty acid synthesis, right? So this is the first step. Again, is for the malonyl-CoA synthesis from acetyl-CoA, and ACC, multi-enzyme complex, is a key enzyme, right, for the synthesis. And again, the carboxyl group is initially from the bicarbonate. And this occurs in the cytosol, right, this reaction. Okay, so now the second fatty acid synthesis complex that involved the rest of the process of a fatty acid synthesis, right? So again, this is also the multi-enzyme complex. Actually, it's even more complicated, and this is actually 2 monomers that they compact together, right, and form the whole fatty acid synthesis complex, right? So the one monomer means that it actually contains 7 different enzymes, right? And this actually identical, right? Identical, but they are arranged in the head to tail arrangement, right? So, but you don't need to remember the whole detail. Just get some sense. This is again the complex of a multiple enzymes, and actually the dimers, and each identical monomers contains 7 different enzymes, right? And because they are arrangement, the tail to head arrangement, so that the complex has actually 2 different ends. One is called a pan-Sal-Hajar group, or pan-SH head, and the other head is cis-Sal-Hajar group, or 6SH head, right? So, and let's see the next slide. Sorry? Pan, well, I guess sorry? Yeah, the molecule is just a different name. You know, the structure is a little bit different. So the cis, like cysteine, has has a cysteine, right? The yeah, and then this is let's see, I can't see this off. You know, this is patterning, right? The group. So it's a cysteine group. So it's a little different in terms of the chemical structure, right? Okay, so and I also wanted to clarify the acetyl-CoA and acyl-CoA that we going to mention later. It's actually two different molecules. The acetyl-CoA I just mentioned, that's actually two carbon molecules, right? And as acyl-CoA is actually even have a longer hydro carbon chain, CH2 chain. For example, the acetyl-CoA, you only have one methyl group, right? And the acyl-CoA, you have R group. R group means CO2, CH2 chain. It depends on which type of fatty acids. If the palmitate CoA, that means this R group has 16 carbons, right? And if some other fatty acids that has 18 or 20 carbons, and this can be different depending on what type of fatty acids. So again, acetyl-CoA just only have a 2 carbon, and acyl-CoA can have a very longer carbon chain fatty acids. All right, so this is the whole process of the fatty acid synthesis, right? They put the first step, ACC carboxylase, and the rest of steps that catalyzed by fatty acid synthesis complex. So first, we already talked about it, right? The ACC complex catalyzed the formation of malonyl-CoA from acetyl-CoA, right? And this just represents a fatty acid synthesis complex, right? The monomer, dimers, dimer one, monomer 1 and monomer 2, and they, have a hat-tail arrangement, and so I have a 2 N, right, cis SH or pan HH and. So the first steps that catalyzed by fatty acid synthesis complex is that, so you can see the acetyl-CoA, first of all, is added to the cis end of a complex or fatty acid complex, right? So this acyl group is coming from acetyl-CoA, right? And at the pan end, the malonyl-CoA then be transferred to pan end of the fatty acid synthesis complex. And the overall, actually, the reaction that you can see on this side, right, the left side. So first step, first 1A, 1B, and 2, actually 3 steps together is called a condensation reaction, right? And then the reduction reaction, dehydration reaction, and second reduction reaction. So all this reaction complete, and then you adding actually only 2 carbons. You only form the 2 the acyl-CoA with the 2 carbons, right? So each cycles, so fatty acid synthesis, the process is actually going the cycles. So one cycles, you only added 2 carbons to existing acyl-CoA molecules, right? So, and for fatty acids, for 16 carbon palmitate, you will need to go multiple cycles, right, to finish, to complete the, the synthesis of 16 carbon fatty acyl CoA. So this is the first reaction, right? And then the second one, so second steps is that you remove the carboxyl group, right, from the pen end, which initially from as monomer CoA, right, by this enzyme called 3-ketoacyl synthase, right? So you remove the carboxyl group from pen ends, and in the meantime, the carboxyl group is transferred to the pen end from cis end, right? So this, again, the highlight with blue is the carboxyl group is from the acetyl-CoA, right? So then as this added to the pen end, so you can see 1, 2, 3, 4, so right, form the 4 carbons, acyl molecules, and this forming so-called carbonyl group. And the next step is the reduction. So we need to remove this carbonyl group. So by adding the hydrogen, right, to become the hydroxyl group, right? So carbonyl group is converted to hydroxyl group by adding the hydrogen, and this hydrogen initially from NADPH, right? So NADPH that needed for providing the hydrogen, right, and for the reduction reaction in this process. And the step 4, the dehydration. So the water is generated by from this, by removing the hydroxyl group, right, and forming the hot water. And this reaction catalyzed by so-called hydroxytase as enzyme, right? And once this hydroxyl group is removed, and this acyl CoA molecules, it become double bond here, right? And because the palmitate is saturated, right? So we need to remove a double bond. So the next step is also reduction again, and this will also need a hydrogen from NADPH. So hydrogen is added to the molecule to remove the double bonds. So eventually you synthesize the acyl CoA, which with 4 carbons, right? So the first cycles, you will need 1 acetyl-CoA and 1 malonyl-CoA, right? So malonyl-CoA has 3 carbons and acetyl-CoA has 5 carbons because you lose the 1 carboxyl group, right, as a CO2. So actually you eventually generate 4 carbons acetyl-CoA molecules after you finish the first cycle, right? Does that make sense? So what you need to remember, I mean, I don't think you are required to remember each specific steps, what enzyme and how, the carboxyl group is formed or hydroxyl group is formed or something like this, right? But just try to remember that for the first cycles, you need acetyl-CoA, 1 acetyl-CoA molecules and 1 malonyl-CoA molecules, right? And you need 2 NADPH, for as a hydrogen donor, right? So NADPH as a hydrogen donor for the two reduction reactions, and you generated 4 carbon acyl molecules. Right? So this is the first reaction, and the following reaction or the subsequent reaction or cycles, just by adding one cycle, just by adding 2 carbons to the existing acyl molecules, right? So for example, the next cycles, you also need you just need a malonyl-CoA, right? And to adding additional 2 carbons to extend the carbon chain, right? So after finish the second cycles, you will generate 6 carbons acyl-CoA molecules, right? Does that make sense? So again, for the following, for the subsequent cycles, you only add 2 carbon molecules at a time, right, to extend the carbon chain, and the donor of the 2 carbon unit is malonyl-CoA, right? Yeah, you have a question?
So it goes through this cycle twice. For the first one, it's acetyl-CoA.
Malonyl-CoA.
And then the second time, it's the acetyl.
Second time, you just need a malonyl-CoA for adding the 2 carbon to extend the carbon chain, right? So, but depend on the length of the fatty acids that our body synthesizes. For example, if we synthesize 16 carbon palmitate, so how many cycles do you guys think we'll need to complete, the 16 carbon palmitate? 8? 7 actually, because the first, you already synthesized 4 carbons, right? So you need repeat 7 cycles, and each cycle add 2 carbons to the existing acyl-CoA molecules, right, to extend the carbon chain. So for synthesize a 1 palmitate, you need to go 7 cycles, right? Your question?
I was going to repeat that. Why, if you have a 16 chain, you need to do the cycle 7 times?
Right. For example, when you finish the first cycle, you already have 4 carbons here, right? The 4 carbon, you already 4 carbons. So you need to do the 7 cycles. So you for the 16, or synthesize the 16, right? Including this first cycles, right? But exclude this first cycles, you actually need 6. You need 6 more cycles, right? So plus this first cycle, so 7, total 7 cycles. Does that make sense? Because you only have 4 carbons formed after first cycles, and you need 12, right? 12 more carbons for 16 palmitate. So you need to run another 6 cycles. So plus the first one, so actually total 7 cycles. Right? Does that make sense? Yeah.
Yes, I'm a little confused from the very beginning that acetyl-CoA, it has 2 different things branching off. It has the acetyl-CoA carboxylase making malonyl-CoA.
Yeah.
And the acetyl-CoA whatever it says there.
Right.
Going to the next step. So these 2 steps are happening simultaneously or separately, or?
Oh, yeah.
So is there more than one acetyl-CoA, or is it both coming from the same acetyl-CoA?
Well, if you're thinking that way, yes. But if we just think a specific molecule, which specific molecule enter the fatty acid synthesis cycles, that.
In this case, it's just one acetyl-CoA.
Right.
And those 2 things happen.
Right. right? Yeah, that's actually a good question. All right, any questions? Okay, so let's take a break.
Or they would be the same though.
Right,
Like,
yeah.
they would be summed together, so you just help things out with them.
And that would be nicer too, because then like they would get to
No, I would do it to help.
and I can't even get my students down to
I know, it's stress, girl. A lot of crap going on.
Okay, let's move on. Oops. So all these steps, right, the cycles actually again takes place in a cytosol, right? Just wanted to remind you again that the palmitate is molecules of palmitate, as you can see, only the first two carbons, which are the methyl end, come from acetyl-CoA, right? The rest of the carbons in the between actually come from the malonyl-CoA. So again, when you run the cycles, carbon donors are the carbon donor malonyl-CoA, right? And also remember that NADH, NADPH is required, right, for the synthesis process and primarily just for the donors of the hydrogen, right, and for two reduction reactions in the synthesis pathway. And here I just give you some idea, where does this acetyl-CoA and NADPH comes from, right? Acetyl-CoA, we know that can be from oxidation of glucose or amino acids, right? And NADPH, I mentioned one sources of NADPH, which is a pentophosphate pathway, right? It's the pathway that generates NADPH that is again needed for fatty acid synthesis here. And the other two sources of NADPH are mainly enzyme reactions and also citrate dehydrogenase reactions. You can just highlight here, right? The Maillard reactions and Maillard enzyme reactions, right? And isocitrate dehydrogenase reactions. Just try to remember three sources of NADPH, and pentophosphate pathway is most important sources, right? NADPH. So counting for substrates, I think it's kind of fun. I don't remember. I probably accidentally asked for information already, right? In the notes. So try not to look at your notes, right? The slide. So how many acetyl-CoA molecules are needed to synthesize palmitate? Two? One or two? Yeah, I think kind of debating, right, that you have a question whether we really need one or two acetyl-CoA. But here I think the one. I explain a little bit, in terms of molecules that enter the fatty acid synthesis cycles, right? We need one that for the first cycle, right, acetyl-CoA. Although you also need acetyl-CoA for synthesis of malonyl-CoA. But actually, I mean, you need more than one acetyl-CoA for malonyl-CoA because for the following cycle, you also need a malonyl-CoA, right? The malonyl-CoA basically is also converted from acetyl-CoA. So what I'm saying here is, the molecules that directly enter the fatty acid cycles, right? So one molecules of acetyl-CoA needed, and how many malonyl-CoA for 16 carbon palmitate fatty acid synthesis. We already talked about, right? How many cycles? 7. So each cycle needs 1 malonyl-CoA, right? So it should be 7. So we need 7 malonyl-CoA for synthesis of 1 palmitate. And how many NADPH? Said 14, right? 14. Right? Each cycle we need 2, right? NADPH for 2 reactions. So 7 cycles and 14 NADPH. And yeah.
So does the first cycle not really count for the NADPH, or is that just for the subsequent cycles?
I think the first cycle counts. First cycle counts. So we,
38 total.
well, we total, I think as overall we actually run 7 cycles, right? So 7, yeah. So I mean, this calculation, just try to help you to understand the whole process, right? How, just general idea, I mean, how fatty acid is synthesized, from which starting molecules, and which are the donors, which is donors, and how many cycles, and each cycle you're adding 2 carbons, right, to extend fatty acid molecules, something like this. So, okay, so elongation of fatty acyl-CoA. So if fatty acid is longer than 16, then we need additional steps to extend, right, the carbon chain. So this elongation of fatty acyl-CoA occurs in the ER, endoplasmic reticulum, right? The ER, and it's also the part of the, the one of the intracellular compartment. And so the elongation steps starts with the long chain acyl-CoA. So long chain acyl-CoA is a substrate for elongation, right? And the rest, actually the sum of the reactions is that's requires a similar or same reactions for the palmitate synthesis. So, similarly like in the fatty acid cycles, right? Synthesis cycles. And the enzyme for this elongation is so-called fatty acid elongase complex, right? That's just by, and again, malonyl-CoA is also the carbon donors for elongation, right? So if you add up more carbons, malonyl-CoA always needed, right? So malonyl-CoA is donors, and NADPH is also the electron donor or hydrogen donor, right? Because they actually run the same reactions. So similar, I just don't want it to go through. And since this is a monosaturated fatty acids, we know that many other fatty acids can have a different amount of double bonds, right? The unsaturated fatty acids. So monounsaturated fatty acid means the fatty acid has only 1 double bonds. And how this monounsaturated fatty acid is synthesized, it seems like a pretty simple. The saturated fatty acids catalyzed by the enzyme called desaturases. So desaturases is the enzyme that catalyzes the formation of double bonds. And in our bodies, we have called delta 9 desaturases. That reaction also occurs in the ER. For example, the one substrate, the pivotal CoA as a substrate, right, and delta 9 desaturase can catalyze formation of a double bond at the 9 carbon positions, right? So the delta, sometimes you have a delta 5 or delta 6 or delta 9. This indicates that the position of the double bond is formed, right, in the fatty acid molecules. So delta 9 catalyze the formation of double bond at the carbon 9 position, right? And we also, in our body, we also have a polyunsaturated fatty acids, right? That means that the fatty acids have more than one double bond. Some have 2 double bonds, some fatty acids have 3 or 4 double bonds, right? And for this, the fatty acids can undergo multiple steps. First of all, you need to elongation, right? Elongation steps, and you stand, the carbon chain, and then the desaturations, right? The desaturase, catalyze formation of double bonds, and we have, delta 4, 5, 6 different type of desaturated catalyze double bonds formation at a different location or different position of the fatty acids molecules, right? So you can see. I just wanted to mention that this numbering system, you probably all, sometimes you will see, like we just mentioned, like delta 9 or delta whatever numbers of the desaturates. And sometimes you also see omega-3 or omega-6 fatty acids, right? So and we're also going to talk about the fatty acid oxidation. We call it beta oxidation or alpha oxidation, so just wanted to be clarified for this different kind of naming system. So we actually totally, in the literature, we have 3 different numbering systems. So alphabetical system, like 1, 2, 3. Basically, the carbon atom are numbered from the carboxyl group. So the first carbon as a carboxyl group are named 1, and then the second will, carbon next to the first carbon are named 2 and 3, right? So started from the carboxyl group. And we also have an alpha, beta, gamma system, and the carbon that is adjacent to the carboxyl carbon, this carbon, the next to the carboxyl carbon is named alpha carbon, right? And then beta and gamma carbon. And last one is the omega system. Omega system, actually, we started from the methyl end, methyl carbon. So first carbon at the methyl end is named omega 1, and then omega 2 and 3, right? So just to clarify this different name system. Okay, so now let's talk about the regulation of lipogenesis. So let's just give you overall pictures of how lipogenesis can be regulated by diet. While we mentioned the high carbohydrate diet and high fat diet, they do the opposite, right? The high carbohydrate diet is strong stimuli lipogenesis, while high fat diet inhibits or suppresses lipogenesis. And if you can connect the high carbohydrate with insulin, then you can understand, right? Insulin should be the strong, signal that stimulate lipogenesis. So you couple insulin with the high carbohydrate diet. So insulin, high carbohydrate diet strongly stimulate lipogenesis, and of course the high sucral diets, right, will also stimulate lipogenesis. High-fat diet and calorie restriction and glucagon and inhibits lipogenesis, right? So glucagon, we know that is counter-regulatory hormone, have opposite actions, right, to insulin. So glucagon usually higher under the fasting condition, right? And calorie restriction also, of course, you don't have enough, the energy, so you don't want to store energy. You try to use the stored energy. So this sort of overall regulation of lipogenesis. And if we go to the details, then we can have 3 different categories of regulators, like allosteric regulation and covalent regulation basically regulates enzyme phosphorylation, dephosphorylation, and the gene expression, right, gene transcription level. So again, we mentioned that this ACC carboxylase catalyzed reaction is a key reaction. So we usually talk about regulation that, talk about how hormones or substrate regulate the key enzyme that can control the whole pathway activities, right? So for the allosteric regulation, citrate and long-chain acyl-CoA, these are the 2 important regulators, and these 2 substrates actually regulate the opposite way. For example, citrate basically stimulate lipogenesis, which is reasonable, right? Because if we have a lot of acetyl-CoA that generated from from glucose and fatty amino acids oxidation, that means we also will have more citrate being synthesized, right, in the TC cycle. So that indicated we have a lot of extra energy in the body. So once we have higher citrate levels, then we push the the fatty acid synthesis. So try to convert extra energy to the fat. And long-chain acyl-CoA we just mentioned, right? Remember, we all know that high-fat diet inhibits the lipogenesis. So long-chain acyl-CoA, fatty acyl-CoA kind of connect with or related to the high-fat diet. When we eat high-fat diet, and we usually absorb a lot of fatty acids, right, from the diet. So that makes your blood fatty acids, long-chain fatty acid level high. So under these conditions, that means that we have lots of the fatty acids absorbed. So again, we don't need to synthesize more. So then we inhibit. So fatty long-chain acyl-CoA is important substrate that are related to high-fat diet, right? That inhibits the lipogenesis. And the second is covalent regulation. So regulates ACC phosphorylation, dephosphorylation. So the hormonal factors usually regulates the phosphorylation, dephosphorylation, right? So insulin and glucagon, again, does the opposite and regulates phosphorylation, dephosphorylation. Yes.
So I have a question. So when you say lipogenesis, you're saying lipogenesis or
Yeah. Mm-hmm.
So you're referring to glycogen synthesis?
Glycogen.
No, like glycogenesis or
Lipogenesis. Lipogenesis. I'm sorry. Did I say glycogen? Sorry. Oh, glycogen. Oh, okay, I see. Yeah, that's actually a good thought. So when we talk about, lipid or carbohydrate metabolism, we sort of talk about specifically carbohydrate or lipid. But actually, if we're thinking the comprehensively in the fat condition, when we have when we have a high carbohydrate diet, of course, glycogen synthesis also upregulate, right? Also stimulate. And in the meantime, the lipogenesis also stimulate. So under fat condition, both glycogen synthesis and the lipogenesis upregulated, are stimulated, right? Does that make sense? So just try to, connect all the knowledge that we learned before and to here. Yeah, thank you for pointing that out. And lastly, the gene transcription. So insulin and glucose basically stimulate the gene expression, ACC, right, and glucagon cycle AMP decrease ACC. So yeah, that's just kind of connection between high-fat diet and to lipogenesis by this long chain acyl-CoA levels. And this is a kind of complicated diagram. I just wanted you guys to understand just in a simple way, right? You don't need to go very detailed. I mean, pretty complicated. So just wanted to introduce one more enzymes called AMPK, the AMP activated protein kinase, because ACC, that is key enzyme in the lipogenesis, is regulated by AMPK, right? So for example, when we under the fasting condition or starvation, when we have a lower energy in the cells, and the AMPK can be activated. So AMPK is an enzyme that senses the energy levels. So when we have a low energy, then AMPK is activated, right? And what AMPK does is to regulate the ACC phosphorylation, right? So ACC, once it's phosphorylated by AMPK, and the activity actually goes down. Sorry, ACC is phosphorylated and the activity goes down, right? So and dephosphorylated ACC, the activity goes up. So increase, up and increase, down is decrease, right? So so which actually makes sense, right? For example, during the fasting condition, we don't want to synthesize fatty acids, right? We want to use fatty acids. So the fatty acid synthesis pathway need to be shut down or decreased. So AMPK is the key enzyme that regulates the ACC activity and shut down the lipogenesis. Yes?
To try to sum that up, see if I'm understanding it. Go down by phosphorylating the ACC.
Yes.
That's how it decreases.
Right. So when you see the kinase, kinase, you always, the kinase is the enzyme that always catalyzes phosphorylation of some enzyme, right? So AMPK, again, is a kinase. So then be able to catalyze phosphorylation of ACC. So once ACC is phosphorylated and its activity goes down, right? So that means AMPK can inhibit ACC activity, can inhibit the lipogenesis, right? So this is something I just want you guys to know, right? Is that clear? Right? So again, during the fasting or starvation, energy levels goes low, and AMPK is activated. And AMPK is an enzyme that catalyzes the phosphorylation of ACC. And once ACC is phosphorylated, the ACC activity is decreased. So that way, that lipogenesis can be slowed down, right?
Once ACC is phosphorylated,
Mm-hmm.
Activity decreases, right?
Activity is decreased, right? ACC. Okay, so here is the slide. Just wanted to explain to you a little bit more detail about how long-chain acyl-CoA inhibits lipogenesis. Right? When we have high-fat diet, again, we have a higher levels of long-chain acyl-CoA in the circulation. So how high levels of long-chain acyl-CoA inhibits lipogenesis? So here are the couple of reasons. So first is long-chain acyl-CoA can directly inhibit ACC activities, right? And second, the the long-chain acyl-CoA can inhibit mitochondrial tricarboxylase transporters. Remember, this transporters is responsible for transport citrate from cytosol to from mitochondria to cytosol, right? Basically to transport acetyl-CoA from mitochondria to cytosol for lipogenesis, right? So if long-chain acyl-CoA inhibits this transporter or shuttle, citrate shuttle, then acetyl-CoA will not be available in the cytosol for lipogenesis, right? So this is a second mechanism for how long-chain acyl-CoA inhibits lipogenesis. And lastly, long-chain acyl-CoA also inhibits pyruvate dehydrogenase. And we know pyruvate dehydrogenase is enzyme that catalyzes conversion of pyruvate to acetyl-CoA, right? So basically, catalyze the generation of production of acetyl-CoA. So if this enzyme is decreased, then you also have lower acetyl-CoA levels, right? You have not enough acetyl-CoA available for lipogenesis. So this sort of three main mechanisms for explaining how long-chain acyl-CoA inhibits lipogenesis, which again connect to the high-fat diet. All right. Any questions? Okay, here just give you more, clear picture. The long-chain acyl-CoA directly inhibits ACC, right, in the steps, and then also inhibits, dehydrogenase, and then this shuttle system, right? Okay. So just wanted to summarize that the insulin regulates lipogenesis. So insulin increases ACC activity by direct regulates phosphorylation, dephosphorylation of ACC, and insulin can also increase glucose uptake, right? Remember, in the adipose tissue. So pyruvate will be increased, and glycerol-3 phosphate is also increased. So I think, I'm sorry, here I probably shouldn't list the second reason here, because this basically we talk about triglycerides, right? So and insulin is also activate pyruvate dehydrogenase, so can increase the production of acetyl-CoA, and suppresses the cyclo-AMP levels, right? We know that when we talk about glycogen metabolism, remember insulin decrease the cyclic AMP levels, right? And this will increase, fatty acids and reduce actually the long chain acyl-CoA levels. Does that make sense? Maybe we can maybe come back to talk about it because we have not talked about lipolysis other pathway, right? Let's just forget this for now, right? So the net effect of insulin is actually increase the lipogenesis, right? So insulin increase lipogenesis in addition to regulates ACC activity. I mean, they are also have the other mechanisms, and we can come back to talk about this later, right? All right, so looks like I finished the first. So this just a summary. Yeah, question?
Yeah, can I, so I just have a question with the regulation of glycogenesis.
Mm-hmm. Yeah.
So, it says that the activated protein is a protein phosphatase, and then the inhibitor protein is the AMPK.
Right.
So is it when the activator protein, so why is the activated protein phosphatase?
Mm-hmm.
If it gets activated when it's much harder?
Yeah. So yeah, if you look at this slide, I mean, diagram, you're right. So insulin basically stimulates the phosphatase, and remember phosphatase usually catalyzes the removal of phosphor group, right, from the protein. So basically catalyze the dephosphorylation. So insulin increase the phosphatase activities and leads to dephosphorylation of ACC, right? So then activate ACC. So this is sort of the mechanism, how insulin regulates ACC. Is that something that you're thinking about it? No? Okay. So okay, so we have a couple of like summary, right, slides. I just want you to go through this and see if you understand all this process. Okay, now let's talk about the triglyceride synthesis. So again, it's a different concept, right? So once the fatty acid is synthesized, and fatty acids usually will packed in the triglyceride molecules, right, and to form a triglyceride. So this sort of the reaction, the overall reaction for triglyceride synthesis. So again, we need a glycerol backbone, basically the glycerol 3-phosphate, and the 3 fatty acid molecules, and to form triglyceride, right? And why we need to synthesize, the triglyceride, and very important thing is that we need to store lipids, right? So triglyceride is a neutral lipids that being able to store in the cells, and fatty acids usually like more metabolic active. For example, we already mentioned the long chain acyl-CoA, right? Is the fatty acid type of fatty acids is very active. So metabolic active, that means they can regulate some enzyme activities or pathway activities. So we don't want to this kind of activity happening. So it's one important way is to try to synthesize triglyceride to put fatty acids in a less active way, right, or active compound to store in the cells. And the major site for triglyceride synthesis I mentioned, right? Adipose tissue is a major side, and then liver can also synthesize triglyceride, and muscle can also, does some lipogenesis. The triglyceride synthesis. And in terms of intracellular compartment, triglyceride synthesized in the cytosol, but facing the ER, so very close to the ER, but it's still in the cytosol.
In the cytosol or in the?
In the cytosol, this is the cell, this is the ER, right? So something happening very close to the ER, but still, in the cytosol. So stored primarily in the adipose tissue, right? But other tissue can also store triglyceride like liver and muscle. But major site for triglyceride storage is in the adipose tissue. So substrates of fatty acid synthesis, the triglyceride synthesis. So we know that we need three molecules of fatty acids, right? So before fatty acids be able to attach to the glycerol backbone, fatty acid need to be activated. So this is a step called fatty acid activation. So basically, the fatty acids catalyzed by this enzyme called fatty acyl-CoA synthetase. Fatty acyl-CoA synthetase is the enzyme that can catalyze activation of fatty acids. So basically, remove the the CoA group from the fatty acids, right? Sorry, it's the opposite. So basically, adding the CoA group to the fatty acids, forming fatty acyl-CoA molecules, right? So this is this reaction that called fatty acid activation, again by fatty acyl-CoA synthase. And in terms of the glycerol backbone, the glycerol 3-phosphate is a molecule that directly enters the triglyceride synthesis pathway. So the sources of glycerol 3 backbone, if you guys still remember, when we talk about glycolysis, right? So glycolysis is an important pathway that for glycerol 3 backbone, a 3-phosphate generation. So in the adipose tissue, the glycerol 3-phosphate can be produced primarily from glucose metabolism, right? So in the adipose tissue, but can also from the amino acids metabolism. But again, glucose is primarily, the nutrient that can be metabolized through the glycolytic pathway to generate glycerol 3-phosphate. So this is the one important sources. And the second source of glycerol 3-phosphate is directly phosphorylation of glycerol. So glycerol can also be directly phosphorylated to generate glycerol 3-phosphate. And this reaction requires an enzyme called glycerol kinase. And glycerol kinase is only expressed or present in the liver. So if we're thinking about the different tissues, so in the adipose tissue, the glycolysis pathway is the main pathway that generates glycerol 3-phosphate, right, from glucose. And in the liver, the glycerol 3-phosphate can be produced or can be generated from the two pathways, right? One is glycolysis and two is directly phosphorylation of glycerol by glycerol kinase. So, so now here we're going to talk about the sources of fatty acids. We just talk about glycerol backbone sources, right? From glycolysis or directly phosphorylation glycerol, and the fatty acids for triglyceride synthesis. Here we have three main sources. First is diet. So fatty acids, if you connect it again the triglyceride synthesis to the fat condition, right? Triglyceride synthesis pathway also activate during fat condition, right, and not the fasting condition. So diet is one of the sources of fatty acids, right? We digest, lipids and absorb fatty acids. So this is one source, and then the body stored by fatty acid pool. So sometimes, in our body, that fatty acids can need to be traveled around. For example, I think we just talked about, right? In the fat condition, when liver does a lot of lipogenesis to generate fatty acids, right? And fatty acids, and then synthesize triglyceride in the liver. And this fatty acid synthesized need to be stored in the adipose tissue, right? So this is fatty acids. It's although initially actually from the diet, but it's directly from the liver, right? So I think this still we consider it from the diet, right? And the storage means that sometimes during the the fasting condition, that makes things a little bit complicated. So sometimes during the fasting condition, when our body need to mobilize fatty acids to utilize fatty acids in other tissues. So first of all, we need to break down triglyceride to fatty acids, right, and release into the circulation from the fat tissue. And then the fatty acids being transported to the liver, and liver then converted fatty acid back to triglyceride. And then triglyceride being released by VLDL, and then carry or transport the triglyceride to the other tissue, for example, muscle, and then break down fatty acid again, and muscle can take up, the fatty acid for energy use during the fasting. So it seems a little bit complicated, but just try to remember that sometimes, the stored fatty acids from the adipose tissue can also be used for synthesize triglyceride in the liver. And this triglyceride, once it's synthesized, and not for the storage purpose, but actually for the utilization in the other tissue, like muscle and other tissue, right? Okay, so the last source of fatty acids is de novo lipogenesis, right? In the liver, fatty acid can be synthesized from glucose and amino acids. But again, depend on actually, the fat or fasting condition. In the fat condition, dietary fatty acids definitely is a major source, right, for fatty acid synthesis. And also de novo lipogenesis is also the important source. But during the fasting condition, that the stored fatty acids from fat tissue can be the fatty acids for triglyceride synthesis in the liver. I hope it's not making complicated story. Yes.
This free fatty acid pool you're talking about, it's just when you were saying that you can take it from adipose stores and utilize it for energy.
Right. but they not like directly go to the muscle. They kind of, making a little bit complicated route, to liver and then, yeah. Okay. All right. Looks like we have 5 minutes, right, left. So I think we should be able to finish. So then, once we have triglyceride backbone ready and fatty acids ready, and then we next step is synthesize triglyceride, right? So several steps. Just by adding, fatty acids to the glycerol backbone, and this, I think this also diagram is good to tell you, the two different sources, right? For glycerol 3 phosphate, one from directly phosphorylation of glycerol, and the other from, glycolysis, right? And once you have a glycerol backbone, 3 phosphate, and first you adding the one fatty acids molecules to SN1 position, right? So, and this is the first step, adding one fatty acid molecule to SN1 position of the glycerol backbone. And the second step, you adding another or the second fatty acids molecules to basically fatty acyl-CoA, right? Fatty acid again has to be activated to fatty acyl-CoA, and to the SN2 position, right? And forming the diacylglycerol phosphate. And usually the second fatty acid that add to the SN2 position are the unsaturated fatty acids, right? I guess the first fatty acids to the SN1 position, mostly the saturated fatty acids, right? And the middle one, SN2 position fatty acids, are usually unsaturated fatty acids. Our last step is adding the third fatty acyl-CoA to the SN3 position. Remember that the backbone is glycerol 3 phosphate, right? So at the SN3 position, there is a phosphate group. So before we adding the third fatty acid to backbone, glycerol backbone, we need to remove this phosphate first. So this reaction for removal of a phosphate group generating diacylglycerol here. And the last step is then you're able to add the third fatty acids to the SN3 position, right, and generating the triglyceride. So just wanted to know, the kind of step, right? You're adding the fatty acids step by step and forming glycerol triglyceride. And the last step, actually the key step, right? Catalyzed by this enzyme called DGAT, the diacylglycerol acyltransferase, DGAT1. DGAT is the key enzyme to catalyze the synthesis of triglyceride. All right, so a little bit more stuff. Maybe we can just leave it for next time, all right? Okay.